At this point, I want to talk about chapter 2. Chapter 2 is all about analysis. I have in the chapter 1, we've talked about all sorts of stuff with geometry and algebra of complex numbers. I even kind of skipped ahead just a little bit to talk about some functions, namely f of z equals z squared, square root of z, and e to the I theta we talked about, so the exponential function. And so we've gotten a little bit of a preview. But before we say anything more about those functions, what I want to do is I want to go through and I want to talk about what it means to take a limit in the complex plane. In long story short is that limits in the complex plane are basically like limits that you would see in Calc 3. It's just that you have a function of 2 or more variables, so we'll deal with that. And after we talk about limits, we can talk about continuity and then differentiability, and then the things that go with that in complex analysis. So that's where we're going to start. And since we're talking about limits, we have to get into epsilons and deltas. So this is just a small taste of analysis here. This is the analysis part of complex analysis. So what we're going to do is we're going to start off and we're going to talk about limits of functions at accumulation points. So remember what an accumulation point is. I think that this is the first step when we talk about limits. Let's say I were to have a set G, and it's just some plain boring set like this. And then maybe what I can do is, so I mean, all the points that are contained in that, I don't want to use the word region because that means something, but in that set. But let's say that it also contains some points, like let's say it contains some sequence of points over here, and then eventually the points get infinitely close together, and then they kind of stop here at this purple point. Okay, this purple point is called an accumulation point if no matter how far we zoom in and look at this purple point, no matter what size open disk we have centered at that purple point, if it always contains those red points in the set, then that purple point is called an accumulation point of this set G. Okay, so an accumulation point is a point, and it doesn't have to be in G itself, but it's a point so that no matter how small of an open disk we look at, there's always going to be points of G in that open disk. Of course, any point in this part of the set will be an accumulation point because no matter what open disk we have, it's going to contain some points of G. But here, this is a little bit more subtle. So this is an accumulation point because no matter what size open disk we have centered at this purple point, it'll contain points in G. And it doesn't matter, just to emphasize again, it doesn't matter whether this point is in the set G or not. It would still be an accumulation point. So that's a quick reminder there of accumulation points. So these are accumulation points. Sometimes these are called limit points. This is exactly the behavior that you need in order to define limits, which is why we're talking about that here. And then of course, any point in here, pick whatever point you want. Those are all accumulation points. That's kind of the boring case or the straightforward case. And so let's get into it. So given a function f, whose domain is G and which is a complex valued function. So here we're taking a function f. Its inputs are whatever points we have that are in G. G is some region in the complex plane, or some set, I should say, in the complex plane. Its outputs are complex numbers. So given a complex valued function f, and given some complex number omega naught, and given an accumulation point, an accumulation, I can't spell. What do you expect from a math professor? Given an accumulation point, Z naught, and this is an accumulation point, I should just emphasize, of G, we say that the limit of f of z as z approaches z naught is equal to omega naught if it has the following, so if it has the following property, if for all epsilon there exists a delta such that for all points z in G satisfying the condition that the modulus of z minus z naught is less than delta, then the modulus of f of z minus omega naught is less than epsilon. And I think that this deserves just a pause and then just to think about what this is saying. This is similar to what happens in Calc 1 when you talk about epsilons and deltas, but there's two subtleties here. One is that for all points in G, and so that's to account for accumulation points. So what this is saying is that there's this property that holds in order for the limit of f of z as z approaches z naught to be omega naught. There's this property that holds, but we only care about that property for the points that are within a delta, within say delta of our accumulation point that we're taking a limit of. Okay, so we don't care about what happens for any other points. We only care about what happens for those points that are in G within a distance of delta from our accumulation point. So that's the first subtlety. The second subtlety, and this is one that we're going to have to ponder just a little bit, and this will come up again and again, is that in contrast to Calc 1, so Calc 1 we talk about functions of one variable, and when we're talking about these deltas and epsilons, we're only thinking about them in terms of we have some interval, and we're only thinking about some interval of real numbers. Here, when we're talking about the modulus being less than delta, we're talking about a whole ball, right? We have some ball that's going to have some specific radius, and it's all those points in the ball, okay, that are going to be within delta, within a distance delta of our accumulation point in z naught. That's a huge difference if you think about it, because in order for the limit to be defined previously, you just had to worry about, in Calc 1, I mean, you just had to worry about the limit from the left and the limit from the right. And that's why we talked about those two-sided limits. But here, if we're worried about the limit at a point in z naught, we have to worry about all the possible paths in points of G. We have to worry about all possible paths to z naught. So for example, if we're looking at the limit of, let me get a different color here, but if we're looking at the limit of, say, this point, when you look at a delta neighborhood, you're not just looking at it from one direction or another, you're looking at it from all possible directions. And worse than that, you can also talk about like spiraling in on the point. There's all the possible paths that have this point as their limit that you have to look at when you're talking about limits themselves. So it's a little bit more subtle than what happened in Calc 1, but algebraically the definition looks very similar. So in the next video, we'll talk about an example of how this works in practice.